All right. So two quick answers, Corina. We did some work with Bernd on speculative execution. It was we used asynchronous hyperproperties to verify 7 different versions of speculative execution. Also, one of the no, it's model checking, model checking. Yeah.
Okay.
And then Anthony, we should talk about probabilistic hyperproperties with dynamic cryptographers. Okay. All right. So now let's talk about repair for hyperproperties. This is a motivation slide that I love to show. When I started working on hyperproperties, Bernd has seen this so many times that he. So when I started working on first monitoring hyperproperties, we were writing a paper with my student. And at the same time, I was waiting for a notification of 2 other papers that I had submitted to some distributed computing conference. So I logged into this conference system, management system, which was popular by, in IEEE conferences at that time. So this is like 2016. It's called EDAS. And so these are 2 papers that I was waiting for notification. These are 2 pending papers. These were 3 other papers that I had submitted to other conferences. So the green one was accepted in another conference. Red was rejected. This we withdrew. We submitted the abstract, but we didn't submit the full paper. And these 2, I was still waiting to hear from the conference. But only looking at this, I was able to find out which one of these 2 papers was going to be accepted and which other was going to be rejected. And you can probably guess that easily too. How? Yeah, session not yet assigned. So this column is a public channel, right? It's everyone. So I am a low privileged user here. I should not be able to infer anything about the internal decisions of the chair during the review process. But it seems there was a bug in this conference management system where when the chair marks a paper as accept internally, still it's a secret to me, it sets some flag somewhere that it is expecting the chair to assign the paper to a session for presentation. So this row says session not yet assigned, and this one doesn't say that. So I knew that, oh, this is going to be accepted, and this is going to be rejected. So the secret. The conference management system doesn't really assign papers to sessions. It seems it was a feature in the software. Nobody really used it, but the nice feature was it was leaking secrets. So so it seems when the chair marks papers as accept, there is a flag somewhere that expects the chair to assign it to a session. Maybe or maybe not the chair does it, but in any case, it is leaking the secret information to a public channel. So this is a classic non-interference policy, which obviously this page is violating, and it is a hyperproperty. So if you were not convinced by all the great examples that Bernd showed you, this is a real one that is actually leaking information. Yeah. So so let's develop. Well, I mean, it violates secrecy of decision by the chair. Now, I mean, privacy, secrecy, they are 2 sides of the same coin. So if we develop a very small function that mimics what this web page is doing, so there is a function. So let's imagine you have a local variable decision, which gets the secret decision. And then if it is accept, it writes the title and the session. Otherwise, it just writes the title. And these 2 observe commands are inserted there just to show what is in the output channel. So I don't have to talk about HyperLTL. Thanks to Bernd, I can just directly go here and show you what this policy should be here that this web page is violating. So if as long as the review process is not done, for the same paper title, you have to see the same title plus session, which obviously that page was violating. If you are still not convinced by all the great examples that Bernd talked about about the applications of hyperproperty, let me give you two more. So linearizability, which is the gold standard of consistency conditions in distributed computing, is also a hyperproperty. So all those algorithms in, for instance, about atomic registers that are supposed to be linearizable, those are examples of algorithms that have to satisfy hyperproperty. Path planning in robotic application, those are also hyperproperties, especially when it comes to adversarial path planning. This example is only the shortest path. Shortest path means that there exists one that reaches the goal before any other path, right? All right, so now let's go to repair. So let's imagine we have that small function for the EDAS conference management system. Let's call it program P. We have a hyperproperty phi, such that P doesn't satisfy phi. We want to give these two to an algorithm, and then the algorithm generates another program P prime such that it does satisfy phi. So the first thing that I'm going to talk about is a piece of work that we did with Bernd a few years ago on repairing finite-state programs with respect to hyperproperties. So here we have a Kripke structure, finite state, and I don't know why this keeps jumping. Now we have the Kripke structure, we have a hyperproperty. We want to find another Kripke structure such that the only condition that we have is that the set of transitions of the new Kripke structure is a subset of the set of transitions of the old one. So we are only allowed to remove transitions. A very simple setting. We wanted to study the complexity of this problem with respect to different fragments of HyperLTL. Why is that? Because a lot of interesting hyperproperties come in different fragments of HyperLTL. So for instance, for all is observational determinism, for all exists is non-inference or linearizability, exist for all is non-repudiation, for all exists is generalized non-interference, and so on. We also have cases that have a couple more alternations, especially for mapping synthesis. So different structures of the formula, and then we also wanted to study different shapes of Kripke structures, trees, acyclic graphs, and general graphs. Why is that? Because session-based protocols, which are very popular in security protocols, most of them are tree-shaped, and terminating programs are acyclic. And there are enough number of examples, especially in the security world, that are trees and acyclic graphs. So I'm not going to go through any of the proofs. I'm just going to show you this table, which Bernd and I sometimes call the periodic table, that every computer scientist has to know. So the columns are trees, acyclic graphs, and general graphs. Let's start with trees. So the good news about trees is the repair problem for trees remains in NP. So for the alternation free and exists for all formulas, it's actually L complete. So the problem is relatively easy. For all exists, the problem is P complete. And then for anything else, it's NP complete. Yes?
Why wouldn't you make delta prime empty? What prevents you from?
Yeah, I mean, so yes, the requirement is non-emptiness of the program. So, I mean, you can keep removing transitions until it is empty, but one of the requirements is, no, you cannot synthesize an empty program. Empty program satisfies everything. Yeah.
Is there an openness to input, or can I just choose one trace of the program?
You can choose whatever transition. There is no input-output. This is not reactive synthesis.
Can I choose one trace?
Sure. Yeah. I mean, so if you remove a transition, essentially you're removing a trace.
No, I'm removing all traces except one.
Sure. Yeah. So, and we don't have, at least at this time, we don't have anything on maximality of programs, for instance. That makes the problem harder.
tables. I mean, Nir is referring to the question whether you're allowed to remove input actions, right? And,
yes.
And here you are allowing, I think, removing input actions, but in the controller synthesis version of this table, you're not.
Right. So we have in another paper we have for controller synthesis, there are transitions that are controllable and non-controllable, and you are not allowed to touch uncontrollable transitions. This is only for what we call it repair, which allows you to remove whatever transition that you want.
Empty programs that don't satisfy essential quantifier.
No,
programs satisfy everything. That's not true.
That is true. Yes. So for universal properties, it satisfies all universal. Yes, correct. Yeah.
Now it doesn't satisfy.
Yeah. All right. Now, having said that, Nir, back to your question. For controller synthesis, the landscape is more or less the same. So for trees, everything is in NP. For acyclic graphs, everything is in P space. And for general graphs, we are in non-elementary domain. There is slight difference here for trees and acyclic graphs. There is a slight shift here. For instance, for all exist, the controller synthesis is NP complete. Here it's P complete. But the landscape is more or less the same. Okay. All right. So finite state programs are sometimes boring. So now we have to do it for infinite state programs. And this is also joint work, again, with Bernd and our brilliant students, Raven and Zohan. Raven at CISPA and Zohan, who's my student at MSU. So the overview of the approach is the following. We have a program P, and we do symbolic execution as an overall approximation technique. We generate a bunch of constraints for the from symbolic execution and also the HyperLTL formula. Then we run SyGuS on it, and we repair the program by generating SyGuS constraints. Now we have two approaches that I will go over them quickly. One is called transparent repair, and the other one is iterative repair. And if I have time, I'll go through some of the case studies. So step one, program semantics. We have a very small grammar, skip, if, while, sequential composition, and observe. The semantics of them is just the general inference rules for the semantics of these instructions. SyGuS problem is that given some function symbols, a set of SMT constraints, and a grammar, we want to interpret these functions such that when we replace the vector, the functions by the vector of solutions, it satisfies the set of constraints given the grammar. So for example, you have these constraints where we know that f of x and y is greater than x and greater than y, and it's either x or y. So it's just the maximum of the two. And if this is the grammar, it will synthesize if x is less than or equal to y, it's y, otherwise it's x. So that's what SyGuS can give us. Step three, symbolic execution. So we are dealing with symbolic configurations where nu is the symbolic state of the program, beta is a sequence of symbolic stores for the observations, as we annotate in our program by the observations. And alpha is a first order formula that records the current path conditions that symbolic execution returns. And of course, you have a sequence of them, which is basically the symbolic execution of the state of the program. Step four, we encode the HyperLTL formula. The first step is given a HyperLTL formula, we encode the inner LTL formula as a finite state machine with an acceptance condition, which is the standard technique. Nothing really exciting there. It is, of course, done by the symbolic state of the program. Then we encode the quantifiers. So the existential becomes a big disjunction, and the universal becomes a big conjunction of all the symbolic paths. Step six is now putting everything together. So now we want to encode the repair problem as a SyGuS problem. So the grammar, the instructions are now in terms of functions that SyGuS is going to find. Then we encode the HyperLTL formula. We formulate the SyGuS problem. We give this to an SMT solver, and then the SMT solver returns the result constraints that when we replace them over the functions, it gives the repaired program. So back to our example. Let's imagine this is the program that we want to repair. So Q is going to be the repaired program. F is the function that wants to repair this area. The set of variables are phase, title, session, and decision. The path condition is obviously for if then else statement here is accept or not accept, and the symbolic paths are one of these two. Now, let's simplify the formula a little bit. So we just want to enforce that at this point, in the next step, which is from this observe to the next observe, the titles that are printed are always the same. So this is a more strict notion of non-interference only by a safety property, just for illustration. And what SyGuS here returns is that always change the local representation of decision to reject. And in that case, the title will not change, right? So it is not changing the secret. It is changing the local store of decision here. And in that case, you will always go to the else statement, and you will always print the same title, no session. Now, this is actually pretty close to reality in the review process. Just go for reject. I am particularly annoyed by a recent NSF rejection where one of the reviewers said in the set of weaknesses of intellectual merit that some typos, for example, what does the square mean in figure 11? And square is our always operator. So yeah, that's what we do in the review process. A few years ago, Moshe told me what we should do in a conference is we just randomly pick papers so people don't take it personally. I have a more deterministic solution. Let's just reject all of them so that nobody takes them personally. And in fact, SyGuS is proposing the same solution. So that is too restricted. Let's talk quickly about two solutions. One which we call it transparent repair. So we borrowed this notion of transparency from the runtime enforcement community. And the idea is that we want to keep the good behavior as much as possible, in the sense that if so we don't want to remove the good behaviors, only the bad behaviors are supposed to be manipulated during repair. So this huge formula, all it says is Q, which is the repaired program, should only repair traces from P which are causing the violation of the formula, right? So this has, unfortunately, a problem, which is in the context of hyperproperties, the bug is not only with respect to one trace. It is with respect to pairs. For instance, for observational determinism, it's with respect to pairs of traces. And if you fix one, it may be too strong. So for instance, if you show always the title of the paper and not the session at all, that fixes the problem. But that may also restrict the good behaviors of the program, right? So for example, here, when we do the transparent repair over that EDAS example, what it does is it repairs it as follows. So if the decision is accept and the session is not empty, then it deems the decision as reject. Otherwise, it deems the decision as it is. So this is the SyGuS approach is not transparent. This is a little bit better, but it's still too restricted. Now, what we want to do is in an iterative loop, we want to search for better and better solutions. So what we do is we have this notion of iterative repair, where we consider three programs: the original program, the repair program, and something in between. So we have P, the original, Q, the repair program, and S, which is the intermediate program. And our set of constraints, which we give to SyGuS, is that Q should preserve all behaviors that S, the intermediate one, has preserved from P. But Q is strictly better than S, meaning that it preserves at least one more behavior from P. Okay, so it is a better solution, and that's what we mean by better, and that's our idea to come up with a notion of closeness to the original program. So when we do that, we get this solution. So in the first round, this is our first repair. When the phase is done, the local decision is the secret. Otherwise, it's reject. But that's not too good. In the second round, what we get is, in the second repair, is that if the review process is done and the decision is not accept, then decision is decision. That means accept or reject. Otherwise, it's reject. This is a much better solution than the first round of repair. And we observe that in most of our case studies, that after a couple of rounds, we get better solutions. So I don't have much time. This is the overall description of our algorithm. Let me quickly skip that. So we conducted 3 sets of experiments here. One was from security papers. So we picked programs that in security papers, like in NDSS, CSF conferences, that they want to enforce non-interference policies. So in infinite state programs, we don't really have a good notion of scalability. We don't really even know what that means. For finite state programs, you go with the number of states, right? Here, we can't really quantify scalability, other than, okay, let's look at the benchmarks that people use in security papers. So this table is from those examples. The second table are from verification domain, where we just took examples, benchmarks from papers, mainly from CAV, that attempt to verify information flow security policies, which are hyperproperties. And this is still jumping on me. And in the third set of case studies, we actually look at functional instances of popular examples from program repair. And these are published mainly in software engineering conferences. So in all of these cases, our approach returns a solution within very reasonable period of time. So let me conclude. I talked about this problem, program repair for hyperproperties. We looked at finite set programs, which we mainly looked at the complexity of the problem for different fragments of HyperLTL and for different shapes of Kripke structures. And we also looked at a SyGuS-based approach for infinite state programs. There are a lot of interesting future avenues, asynchronous hyperproperties. So for instance, speculative execution, repairing those would be very interesting. What I hear from folks in the security community is fixing or even verifying concurrent programs with respect to information flow security policies is a very much unsolved problem. And then attempting repair is even more interesting. And of course, in reactive settings. Thank you very much.
Questions?
It's not clear to me why this iterative repair with SyGuS will lead you to the end to, I mean, you can do it and you get something, but I don't quite see what can you say formally about what you're getting.
What do you mean by formally? So we have...
You're running experiments, you're getting some good results in some cases, maybe not in other cases.
Yes, that's life. So I'm not sure what you mean by formal guarantees.
I mean, you have some, it seems just very empirical. I mean, I don't know what you can say other than I have a method that works sometimes.
Sure. I mean, first of all, this is a heuristic, right? It's not complete for sure. It is sound, but not complete.
When would you know that you're okay? You know, you're repairing, you're doing iterative. How would you know that that you have a good result?
I think another way to ask this question, how would I know whether the repair that I'm getting is a reasonable repair?
Yeah.
So we try to answer this question by this notion of closeness of the repair program to the original program. So we try to remove things as least as possible.
Okay, but?
Now, is this minimum repair? No. Is this, minimum repair? No. But at least if you want to call it empirical, I'm fine with that. But at the same time, if you want to have some notion of closeness, formal notion of closeness, at least what I know from my work on LTL repair, the complexities are much higher. I think Bernd wants to add something.
Yeah, I just wanted to answer to this question, what can we formally say? I mean, the space of repairs is a partially ordered space, right? And there is no guarantee that there's a global optimum. And this approach will run towards a local optimum.
Yeah.
This is the guarantee. So when we've reached the local optimum, we'll terminate. And it could be that takes a while, but we'll work towards the local optimum. That's all we can say.
Yeah.
What does your algorithm do when the answer is negative?
Right.
No, I mean, if you, for example, split the states, this may solve it. So are you trying things like that?
No, we don't do any refinement. So I guess what you're saying is if we cannot repair, then what? Currently, we don't do anything. Now, one thing that you can do is one of the steps is first localize when it has to be repaired, right? You can change that and hope for a better solution.
So I have a question. So your version for infinite state system, it looks like a little bit like you're inventing Sketch, essentially. So why not just, like what I like is that you find some notion of minimal, but as Moshe said, you pick one notion and stuck with it, versus if you put yourself into a framework, I think of Sketch like kind of as a programmable framework, then I get to decide what's my notion of minimality, because I can use the optimization objectives built in Sketch, and then I can look for my notion of minimal. So why not just encode the entire repair problem sort of as a meta problem in Sketch, and then have a programmable quantitative objective?
It's not that easy for hyperproperties because you're dealing with multiple executions. If this was only for functional properties, it is much easier to define that notion of minimality. That's why Bernd was talking about local and global optimum. But I mean, imagine in the EDAS program, I mean, one solution which is not optimal at all, is to always show the same thing in that session column. Now, is this optimum? No. How would you even characterize minimality here? Because we inherently think about single executions. How do you characterize minimality for multiple executions? We have sort of similar problem in the probabilistic case, where when you have a sequence of scheduler quantifiers, I mean, in MDPs, there is a notion of minimal maximum scheduler. But when you have a sequence of them, what does that even mean? So sure, I mean, you can specify it yourself. That can be done.
Yeah, but maybe I'm gonna try to channel my colleague Tom Reps here. Like, it's like you built an algorithm for a solution for a specific problem instead of a framework. So I think like what perhaps would be interesting to have is a SyGuS for your problem, not a solution using SyGuS of a version of your problem. So there should be a search space.
Yeah, that is a great point, and I think that is something that we have to explore. Yeah. That what does SyGuS mean, or what is another notion of SyGuS in this context? Sure, that would be very interesting, and we did think about it for some time.
It's called SyGuS and SyGuS.org.
Okay.
But just an advertisement here. But you can encode hyperproperties in that.
Okay, we should talk about that.
Hi. Here.
Yes.
So, you talked about the complexity for the tree base and the general and acyclic. So the natural question is, if you bound the tree width, so do you have parameterized complexity algorithms as well in
we
between?
don't.
It doesn't work, or you don't have it?
So that's like bounded synthesis, right?
No.
Bounded?
Bounded tree width. I mean, do we have complexity results in between trees?
Oh, no, we don't.
If you can get it to work for trees and then for general you have, wouldn't it be interesting, because you seem to have practical instances, so they probably have some nice structure. I mean, usually, I don't know.
Sure. I have nothing against it. Sure.
Okay, so now that Borzoo and Ben have lots of work to do on, let's thank Borzoo once again. This ends our morning session. So our next session will happen online. So Rajiv confirmed that he will join. Unfortunately, he's one of those people whose flight last night got canceled. So he didn't still manage to come, but he will join online and he will give his talk online, followed by Suguman, who will also give her talk online. And now we have lunch. You are free until 2. I don't, that lunches won't be served outside, so I don't know where to go, because this is my first 3 hours at Berkeley, so I cannot give you any recommendation except ask people, hey, have you been here before? And follow them to the lunch. It will be here, so just come here.